Okay, few students came. All right. Ajan Amulia, right? No. The attend the orientation. Okay, good afternoon to you all. We have 1, 2, 3, 4, 5 students. Let me share. Good afternoon. My screen. Where are we? Can you see your reports grades? Some students in the morning session, they couldn't see the grades. Last week report I graded already. Can you see it on LMS?
Yes.
Okay.
Yes, Ajahn.
So most of you did well. Yeah, I kind of like expect you to submit reports like this. There were 2 questions that a lot of morning session students got it wrong. I think few of you also got it wrong, or you just didn't answer or skip. The first one was the first one. Let me think. Oh, the first one was about the coming up with the general formula. Okay. For the number of bits required to hold a quantity in binary number. Okay. So let's say I want to store the value 5 in binary. Okay. If I convert it to binary, it's 1, 0, 1, right? Yeah, 1, 0, 1. So if I want to save this, I need 3 bits, right? I can use 4 bits. This is one extra bit here, right? But it really doesn't hold any information. It's not necessary. Can you see the point? It's not necessary. I can have 1 million bits, but it doesn't matter. For 5 to be stored in binary, I just need 3 bits, okay? Minimum number of bits. Now, what? Don't do. What if I want to store 15? Then 15 is 1, 1, 1, 1. I need 4 bits. Okay. How about 16? You see, this is the borderline. This is the crossing. Okay, there is a crossing here. All of a sudden, for 16, which is 1, 0, 0, 0, 1, all of a sudden, I need 5 bits. Okay. Then it goes all the way to 31. I still need 5 bits, but this is the crossing. When 31 becomes 32, all of a sudden I need 6 bits, right? So when I want to come with general formula, I kind of know that there must be 1, the quantity 1 in the formula, maybe plus 1, maybe minus 1, okay? Because I can see these borders here that, you know, the formula want to give me the answer 4, or the answer 5, or the answer 6, okay? So here, if this thing goes plus 1, it gives you 6. If it goes minus 1, it gives you 5. Can you see that? Does it make sense? So I kind of can guess, if I have a little bit of IQ, that there should be this 1 in the formula, okay? Now, another, another thing that we also should remind ourselves is the logarithm. So if you have logarithm, let me drink some. I talk for 3 hours in the morning. So the log of number x. No. Let's look at the power first. So we have a to the power of b will give you c. Okay. Now I can actually express this relationship, okay, using the log. So the log of c base a gives me b. I think you learned this in high school and maybe calculus. I don't know exactly when you learn this one, okay? So we actually can convert this to this, right? Both of them are the same thing, but this is log, this is the power. I give you a numerical example. For example, number 2 to the power of 3 is 8. Then I can say the log of number 8 base 2 is 3, right? Okay. Now, in the morning session, I try to calculate this using the Windows calculator, but I really don't know. I asked the students how to do this. They didn't know to. You see in the calculator, right? There is a log button here. Can you see the log? But this is log base 10. Log base 10. So if I press 8 and then log, I don't get the 3. I get the base 10. Okay, which is another thing. I don't want it. There is ln2. This is base e. So instead of 10, you have e. But what I want is base 2. So I don't know how to do it with the calculator. If you know, let me know. Is there anybody knows how to do this? If we don't have a calculator that can compute the log of a number in base 2, then we can actually use Google. Okay, so log base 2 or log base 2 calculator. Okay, now with this one, if I have, let's say, 8 calculate, I can get the 3. Now this is the right one that I want. Okay, this is base 2. You see, base 2, log base 2 here, base 2. Okay. So I try to run some experience, like, let's see what is the log of 15, okay? Log of 15, calculate. And it gives me 3.9, okay? That's the answer, 3.9. And I start to think, I know that the correct answer, the number of bits needed to hold the 15 is 4, right? 4. And here I got 3.9 something, right? Then I kind of like, you know, it doesn't make sense. I cannot say we need 3.9 bits. It doesn't make sense, right? 3.9 bit. To hold value 15, we need 3.9 bits. It doesn't make sense. You either need 3 bit or 4 bit or 5 bit or 10 bit, okay? So it cannot have any decimal points. Now, I start to think, what if I round down? So 3.9 round down becomes 3. And then you see, I told you there is a 1 in our equation, right? And plus 1. You see the point? So this is still, I'm not sure if the, stop. If this is the right formula or not, okay? I stop biting. Stop biting. So, yeah. So you see, I said the number, the given number is x. Okay, the log of x base 2, and I want to round it down. So the mathematical symbol for that is this. Okay, it's a bracket that doesn't have this, and this is the bracket, right? But it doesn't have the higher part. So this rounds down. Okay, so and plus 1. So let's plug the 15. 15, it gives you 3.9. Round down gives you 3 plus 1 is 4. 4-bit, that's the correct answer, okay? That's the correct answer. Then how about 33, which is another number that I told you, right? So I come here, I said 33, calculate 5 point something, right? I round down, it becomes 5. Plus 1 is 6. We need 6-bit, is it correct? Verify, I come to my Windows calculator. Power of 6 is 64, yeah, correct. 64 is greater than 33, right? And then it can hold it. But the next value is 2 to the power of 5, 5-bit, which is 32. 32 is actually smaller than 33. It cannot hold it. So it's kind of like, I think, so most of you did not come up with this formula. I don't know why. It actually needs a lot of mental practice, you know, and patience. I also could round up and subtract, right? Maybe, I'm not sure. But I think round up, subtract is also another option. So this is the general formula. Question number 3, many students missed it. Another one was, what was the other one? It was I asked you about the purpose of resistor that you put after the LED. So we have LED, right? And then here, in the first experiment, with number 0, we put the R. Then I asked you why. Most of you actually answered correct. The answer is that we want to limit the current. So you have to actually write this, to limit the current that goes through the LED. Okay, that's kind of the answer. But then what is the value of R? How can I calculate the R? Okay. Then at this point, actually, I think many of you failed to show me the calculation. And this is important, very important. So I know that if I connect this to VCC, then this LED will be on. If I connect it to ground, then this will be off, right? VCC, usually we are dealing with TTL. So VCC is kind of like 5 volt if you use the TTL technology. So let me get rid of this. So this is 5 volt. And then you apply the 5 volt, there will be a current, okay, I, going through this LED, right? Now, let's see what happens if the R, if we remove the R, there is no R. So R is 0. And the simple formula you learn at high school, the Ohm law. B is 5 volt, right? R is 0. I. How to find the I? I equals to 5 volt divided by 0. Now, this is actually a little bit tricky because if I use my calculator and I put 5 divided by 0, cannot divide by 0. That's the answer, okay? So this is actually undefined. And look, but you know, I kind of want to know what happens when the R is 0 or R is very small. Okay, very small. So I can, you know, run an experiment like this. I said, how about I just put a very small value? Okay, let's try. So 5 divided by 0.0000000, something like this, 1. Okay, boom. 5 divided by 0.00000. Yes, you see, I get something very big. Equals to this. So as you see, the more the R is small, the larger the value you get. Okay, and that's actually the meaning of the definition of limit too, when they want to teach you the limit. So when the R approaches to 0, the I approaches infinity. Okay, so that's why this is actually infinity, or in computer they say, oh, we cannot divide by 0, so it's not defined. But the point is this, the I will be very huge, very huge. Now, here the VCC comes from where? It comes from a power supply, right? Power supply. Now, this power supply is something like this. You can actually buy a power supply for the laboratory. It's something like this, yeah. Okay. Now, every power supply has a wattage, has the amount of power that it can deliver. It's like an engine, like, you know, like a driving force. Okay. Now, for example, for this one, it says I can deliver 30 volt at maximum 5 ampere. So this power supply can give me 30 times 5 amp equals to 150 watts. Okay, not more than that. This is the power that it can give you, not more than that. Now, if I connect this to connect this thing, right, to that power supply, then this is 5 volts. Okay, it can give me up to 150, right? But not more than 5 amp. More than 5 amp is not possible. Is not possible. Okay, but so the power supply actually will stop here. 5 volt, 5 amp. Okay, this is actually 25 watts. So you're gonna have 25 wattage, okay, on this, on this LED, 25 watts. Okay, so then you have to ask yourself how much heat you're gonna generate. Now, you remember the bulb lamps that you had when you turn them on, you cannot even touch it. You remember? You could not even touch it. It's just so hot. If you touch it, you burn your skin. The temperature is maybe more than 100. So the LED, if it doesn't withstand this, it will burn. It will burn. Okay. It cannot withstand 5 amp. It's too much. Too much, because the power dissipation, the heat dissipation, the heat that is produced here, will burn the device. Now look at the how it happens. Observe LED burning. Typo. Yeah, you see. So this is actually what happens if you try. If you try the resistor. Okay, Lazada is actually cool. You see, now there is no resistor. Why is it blurry? It's blurry. This is blurry on my eyes cannot see. It's blurry, right? But this is the LED. You see? Yeah, it will die. Bang, dead. You see? Did you see the glow? It glows. Now, I remember one student also gave me another one. Maybe I have to go there to the chat room. Hold on. May I what? Repeat? For this one? This guy is talking. I was talking, one student is talking to me. I was like, what is this? This YouTube is being played. Funny. Hold on. So what I want to show you is another LED Teams. In morning session, one student share. Oh, this is the afternoon. Yeah, here. Let me see. That was a good one. Another student morning session found. Oh, it's not here anymore. Why? So, see previous replies. Oh, here. Okay, this one. Watch this one. Yeah, this is actually the nice one. Look what happens. First, can you see there is a gap here? Can you see that? Okay. Now, because of the high current, there will be an arc, and you see the arc, and then, ooh, wow, and this is the smoke. It depends on the material of that LED, okay? So anyway, my point is this, that if you don't put the resistor, you're gonna burn this, okay? But what is the value? This is also a lot of students did not mention. Yeah, this guy is cool too, evil. Watch this guy sometimes if you have free time. Anyway, so in order to know the correct value of the resistor, you have to actually go LED and look into the data sheet of an LED. So it depends on whatever LED you buy. There is, for example, this one. Okay, so this manufacturer, what's the name? Farnell Network. Okay, Multicom, whatever. Okay, they say, all right, we have a product for you. These are the dimensions, right? And somewhere, you have to look here. So you see, it says continuous forward current. Means if you want to operate this component continuously, means non-stop, 24 hours, non-stop, always on. What's the maximum current? 20, the unit milliampere. So that's the maximum. Now we want to have a margin. So instead of 20, we set the 15. So back to here, we say, now V equals to Ri. Now V is 5 volt. We want the R, and the maximum current allowed is 15 actually milliamp. It's not 20. We want to have 5 milliamp margin. So the R is what? 5 divided by 15 milliamp. 5. Now the engineering calculator that you should have, they have some keys for the unit. So you just have to press 5 then 15, and then there is this M, right? You know about this, right? Is there any student who doesn't know the Casio? Let me show you. Casio calculator. Yeah. Image. Yeah, this one. You should buy something like this, okay? Does it have it? Oh, this one doesn't have, no. Don't buy the FX 350, buy the 900 something. So 900, 950 maybe, something. Now it's so cheap, I cannot believe. Yeah, not this one. Huh? Yeah, maybe this. So there is an M button somewhere. Let me see if I can see. Where is the M? Where are the units? This one doesn't have. Oh my God, really? Can you see it?
Then into 10x that button.
This one doesn't have, but you know what I mean, right? This actually should have a, okay. Maybe this one. This doesn't have. They don't have. Oh no. Can you? If your calculator has it, can you give me the model? Maybe this one. No. How about this? This one doesn't have. Casio FX 9980 plus. Maybe. Yeah, maybe this. Oh my God. How come they don't have? You see, they should have. This one doesn't have. Okay, let me see. Okay, hold on. I go to. I don't know even where is mine. Let me see. If your calculator have the M, means macro, this symbol. Where is it? You see, it has M macro. Okay. Sorry, milli and macro and N nano. It should have these symbols. Some of them have. Let me see this one. This one doesn't have. No. Yeah, you should buy the ones that actually has it. It will be very easy for your exams. Maybe this one. This one doesn't have. Oh my God. But I remember when I was a student, was it Casio? It was Casio. Casio. How about this? No. Anyway, but this is 750 and it doesn't have it. Casio. Calculator. Let me find for you, okay? It's very actually scientific. Very handy. How about this one? I cannot see. Anybody here with that kind of calculator? Not this one. Okay, maybe this. Maybe this. Let me see.
Ajahn, I sent it.
You sent already? Let me see. Okay, FX9. Yeah, this one. Yeah, this one. 991 MS. 991 MS. Okay. Yes, I think this one. Yeah. This one actually is, you see, it's cheap. It's 600. This one should have. Yes, you see, it has. Yes, this one has. You see, number 5 is M. Number 4 is means milli. Okay, number 4 is macro. Can you see that? Macro. Number 7 is mega. Number 8 is giga. Number 9 is terabyte. Can you see the capital T? Yeah, this is the one. Get this one. So when you want to use it, I think you have to press shift. Am I correct? Yes. Can you see the shift, the yellow shift up there, up left corner, next to the alpha? So you just press that one. So basically what you have to do is this. Come back to our calculation. Oh my God, we are like 10 minutes. So you press the 5 and then divide and then 15 and then shift and then M. Okay. It automatically adds 10 to the power. M means milli, right? To the power of -3 automatically for you. You don't need to type. It's very handy for your exams. Okay, so if you do it, and let me, but you know, even my Windows calculator, it doesn't have it. It doesn't have it. You actually can download a lot of advanced calculators. Some of them are even paid. Anyway, so 5 divided by this. Okay, now I do like this because I know. But in the exam, you know, if you do like this in your head, then you might make a mistake. So what's the answer? This is the answer. So this is the answer. What's the unit? Ohm. So you actually should have a resistor with 330 ohm. And now you know why when you go to the register to buy resistors from websites, right? You can see this value. Now you know why. Because TTL is very usually people want to drive the LEDs using 5-volt TTL, and then they actually they go through the same calculation that we went, and then they got this 330 ohm, and that's why they buy the resistor 330 ohm. Now, if for example, you come in our lab, maybe we don't have it, then what you should do, you should go for the nearest, closest resistor, like 500 is okay. But even 1K is okay. But then if you put 1K, you will see your LED becomes dim. It's not bright anymore because the current now is low. It doesn't shine, okay? So you have to do one final project for this course. And I see every semester, the students, when they want to present their project, the LED or 7 segment, let me show you the 7 segment. 7 segment is the same thing. It's just a bunch of LED segment. It's like this. I know everybody knows this is right. We will learn about this too after a few weeks. So this is the same as LED. It means it needs resistor. You have to control the current. If the current is low, this 7 segment will be dim. So every semester, people come with their project, and the project has these 7 segments or LEDs, and they don't work. They're like very dim, and they say, Ajahn, can I turn off the light of the laboratory? We have to turn off the light to see it. Now you know what's the problem, right? The problem is that you just put so huge resistors that the current cannot go. And when the current cannot go, the LED will not be bright. Or maybe the 7 segment, you broke the 7 segment. By how? By forgetting to put the resistor there. And then you try it a few times, and now it doesn't work anymore. So you have to replace it. Now, another thing is back to the data sheet. After this, I will check attendance. Data sheet off. Yes, this one that your friend sent, right? How much you bought this one? This is the best calculator. If you buy this, right? So dirty, man, dirty. Wash it. Wash it with alcohol. It's all COVID-19. So, Kongsu, full of COVID-19 here.
I think I used too much.
Yeah, I know. You can, if you buy this, it will last for 10 years. You can even give it to your son or daughter. Really. It's very tough calculator. I really like it. I really highly recommend this one. FX991MS. Yeah. Perfect one. Perfect. Yeah. Every one of you should buy this. Let me see how much is it. Oh, it's only 650. 650 is the best. I have two of them. You can even buy from Lazada. Oh, this is Lazada. Yeah, that's why. If you buy from somewhere else, I think it's around 900. Lazada is cheaper. They produce this in India. High quality. From India to Thailand, I think, yeah, maybe 3 days you can get it. Very nice. Anyway. Yeah, I really got, a few years ago, I ordered this from Lazada or eBay, I don't remember. And it came from India to Thailand within 2 or 3 days. I got surprised. It shows first the Indian postal system is accurate. It shows that one because there are two sides involved. One is the country of India, another is the country of Thailand. And the Thailand postal system is very fast and accurate. And the whole system, is like amazing. It's like I got surprised. Now, I think maybe in many things, India is number one already. Maybe in software is now number one. Many things. Okay. Anyway, whatever. So now let's talk about what I wanted to. Oh, okay. Let's go to the datasheet here. Oh, no. Here. Okay. So now the LED has another parameter. Look at this. It's peak forward current. Okay. Now this is the same forward current. Okay. But it says, listen, I'm gonna reveal to you a secret. My device can actually accept 5 times more than the max continuous current. You see, this is 100, right? But for a very short period of time, only 0.1 millisecond, okay? Means only one, imagine 1 second, right? You divide it by 1,000. Only one of those 1,000 time periods is actually very short. Do you understand? Okay, but it says this is the secret. If you want to, have a very shiny, like a flash, like a flashlight, right? Then you actually can put 100 milliamp into this, and that's actually your cell phone, right? How the flash of your cell phone works. Yeah. So there is a capacitor in your cell phone that is charged, and then, but very short. That's why flash is like very short, right? It's just 1,000 1,000th of a second. Divide 1 second by 1,000, and that's it. That's the flash for your camera. Okay. So a lot of current goes through that LED, and then you have the flash. So here is the same thing, but this LED is not used for flashing, okay? But you should know. That's why a lot of, for example, the remote controls, a lot of things, right? They don't keep their LED on forever. It's like you press a key, they just like flash like that, and it's very bright. It's very bright. It's because of this. Okay. Now let's do the attendance, and then I think around 1 hour, like 1 hour 20 minutes, we will go through the lecture note, and then that's it. Let's do the attendance. Open Discord. Audit, are you here?
I'm here.
We have only 4 students? How come? No. Yeah, more. Audit, okay. Elda.
Yes.
L dot. Consul. Natashanam. Okay.
Sir, I believe you haven't checked my certificate for taking leave on my
For the first one?
Yeah.
Okay. So
Then
there is another student, I know, there is another student similar to you. Don't worry. So I just put here J equals to justify. Okay, justify. But it's okay, I understand. So, Siripon, Appeng. How about Korabit? Mr. Korabit, absent. Shashank, absent. Okay. Now, let's start our session. Chula, no. Anyway. Number 2, right? Oh. Okay. All right. Okay. So let's start. So we talk about the logic gates like AND. Okay. And then you went and you found a simulator. To simulate it, you observe the pattern and how it works. We also last week emphasized on implementation of AND. Implementation of logic gates is very important. Because we talk about this, that, okay, you know how something works, but will you be able to make that thing happen in real life? Okay. And if you don't, you still can buy it from other countries. But there will be a point that maybe some countries tell you, no, we're not going to give it to you. Then what's going to happen? You see? So implementation is very important. And we talk about this, that if you can make a transistor, now there are actually a lot of countries right now in 2021 that cannot make a single transistor. Single, I mean discrete, not married or single. Yeah, discrete transistor. So this one, right? A lot of countries still cannot make it. Can you believe that? It's actually because it's difficult. It's not something easy, okay? So this is BC547, is a transistor, single discrete transistor. It has 3 pins, base, emitter, collector. Okay, it's not that difficult, but you know, you have to have a high level of high technology to produce this, mass produce this. Now, if, for example, you have this, now in this class you learn that, for example, for an AND gate, you just put 4 of them together, it becomes an AND gate. Okay. Then if you try to experience and in the labs of your own country, try to work very hard, you might be able to actually put all these transistors and resistors, everything together, and actually build something like this, TTLIC, the one that we have in the lab. Okay. This thing, you might be from that. This is actually the same thing, except that they put the transistors packed together, they shrunk the size, and they put the resistors, everything. Okay. Yeah, the schematic is this. Okay. A bunch of transistors and diode and resistor packed together becomes, this is actually the AND gate, for example. All right. Now, if you can make this, right, then it's okay. You want to buy a very high-tech cell phone or processor or whatever, right? You can buy. But how about if you want to, for example, build military equipment, okay, that need some kind of digital circuit? So let's say FPGA military grade, yeah. So you need a chip like this, okay, like this, that is used in air fighter jets, you see, or missiles, all right, this chip. Why you need military grade? Why? Because the transistor that you make operates at, for example, is designed to operate at room temperature, or maybe from 10 degrees Celsius to 85 degrees Celsius. That's the max, okay? But when you use this in a missile, and then this is the air, right? And you shoot the missiles. Now the missile is here. Here at this point, right, the air pressure changes. Maybe if you exit the atmosphere, the sun exposure, right, will quickly change, so that there's a temperature variation, very high variation. So, for example, from -10, suddenly you go to 300, right? So you have to actually account for this. How the material, the elements that you use to build this device react in this, range of temperatures. Everything will change, you see? So you cannot actually use the normal stuff. Now you want to buy this with the normal components that they sell in the market. You send a missile, your missile here will not operate. It fails. It cannot guide the missile, and then your missile falls. It goes nowhere. You cannot control it. And it is at this point that when you go and you say, Mr. Xenix or Mr. Intel, can I have this chip? Can you give me this? This is military grade. Can I have this? And the answer is no. They will not give you. Can I have this for my satellite? No. So as long as you play, as in the kindergarten, in the play yard, then it's fine. But when things become serious, you will see all those democratic nations that love democracy and freedom of speech, all of a sudden, they become really undemocratic and they will not give you anything. Okay? So you, as an engineer, you really have to build the will to first learn the stuff, plus explore how you're gonna make these things by yourself or by your own laboratory in your own country is very important. Now, somebody might say, this is actually 1960 technology, right? So not the big deal, if we want to make it or not. Well, come on, this now is the world of cell phone and smartphone. Nobody wants this stuff, right? Now, if you search for Apollo computer system, the Apollo, right? They claim, I'm not sure, okay, that they sent a spacecraft and a man to the moon, right? Now, the computer they used in that spacecraft, look at this. 16-bit. It's a 16-bit. Now, your cell phone, what's the bit length of your cell phone? It's 64-bit already, right? It means your cell phone, in the terms of bit, the length of the word length, is four times larger. Okay, and when this is actually very old technology, but 1966. But look at another interesting thing. Now, when you come to the design, right, it says it uses 4100 IC. What IC? Single 3-input NOR gate, TTL. You see? Integrated CPU in Apple. These are the ICs. But this is the surface mount. I forgot to tell you about. You see, when you want to buy the TTL IC, so you have this. Yeah, you see, this version, right? We call it SMD. We call it SMD. SMD. Surface Mount Device. SMD. Okay. Then another version is this one. It's called True hole. TH, through hole. It means it goes through a hole. What goes through the hole? Can you see the pins, right? The pins go through a hole, means the board, right? And then you solder like this, right? Yeah. So all these chips, they are SMD, right? There is no hole, but let me through hole. Yeah, these are through hole. Yeah. So how to show you? Yeah, like this. Okay, this is actually true. You understand my point, right? It goes into a hole on the board. So look at this. Now think about it. What I want you to really realize, to improve your confidence, that actually if you come up with this TTL IC, right, then you actually can control a spacecraft with 4,000 of them. Okay, right? I'm not making that up. It's here. You can read yourself. It's NOR gate. With NOR gate, you can implement any logic gate that you want. Okay, so with this system, you can do a lot of things. Now, if you have the TTL IC, you can actually build the computer. TTL based computer. Based. Gigatron. Oh, there are many. You can actually read this, okay? But I want to show you the picture. Yeah, this is now. So a lot of students, right, when they take this course, they think this is like old and obsolete. Yeah, this is what I said to true hole, you see? So you put the IC and you solder like this, okay? Please put solder, yeah, you see? Oh, yeah, you see? Sometimes you have the IC and you don't want to connect the IC pins. Why? Because if you do, if this IC goes out of order, how are you gonna replace it? You have to unsolder the whole thing, right? So instead, can you see this plastic here? So they have what we call the TTL socket. TTL socket or something. You actually can buy this cheap, okay? And you can put this socket here first and then put the IC, okay? Now this guy is building a computer. Look at that. Look at that. Oh, what happened? Look at this. The guy just using TTL, right? And this is the VGA. Can you see the VGA? This is TTL. TTL macrocomputer, ROM version 1. A snake racer. Can you see that? Can you believe that? So why do we need this? When your cell phone is more powerful than the, hey, it works. The reason is that, it's like to bypassing the sanctions or restrictions that other countries, when they enjoy the higher technology, put on you. You actually can do what they went through and even faster. Okay, so you see now the TTL. This is the old PC game. Yeah, very fun. 8 instruction. This guy is crazy. This guy is crazy. So let me see if I can find another images. TTL based computer system. Yeah, it's look like this. Can you see? With the TTL that we actually, look at this one, this is beautiful. We're actually going to learn in this class. Yeah. You can build a lot of things. Holy hell, look at this one. Ooh, this is cool. Look at this one. Ooh. This is cool. William Bain Space Age. Mixed signal Bourbon, and this is German. This is cool. So yeah, so for example, a lot of countries, they realize that they just can't rely. So they actually, for example, can come up, you see, with a 4 megahertz. I think it's a 4 megahertz processor, 32-bit MIPS 1 ISA. Yeah, it's a 32-bit processor. Very nice. Yeah. So they build this for defense, and because even for example, if you want to, what is that? Somebody says something in chat. Ajan, I have to email this. Yes. Okay. So imagine you, for example, want to control very sensitive devices like what? Like the nuclear centrifuges, okay? Nuclear centrifuge is this device. Looks like this, okay? You see? Looks like this. Now, if you want to control them, right? This is Iran. So they put it on. If you want to control this, right, you need a computer. But what if you buy a computer from outside that doesn't, you just don't know how it works, right? And then exactly at the right moment, they can actually infiltrate and do whatever they want, because they build that thing, right? They know all the negative and positive points. Anyway, so back to our thing, or we haven't even started yet. Oh my God, 1 hour passed. So here today, so you learn all this. This is actually important. It's good that I do well on this, right? So we learn all about this, right? Implementation and stuff, right? And last week, you learned how to use this to come up with what we call Boolean functions, right? Using n and or. But you didn't build it, you simulated it, okay? Today, we are going to learn how to actually simplify the circuit that you designed last week, okay? By simplification, I mean, if, for example, you use 70 gates, you try to shrink it to 50, okay? So you just kind of try to get rid of some number of gates, okay? To save money, to save the transistor, to save the size of the chip, right? There are 3 ways: mathematic, algebraic manipulation, K-map, and the CAD software, CAD. Now, in old days, engineers sit down and pencil and paper, and then they calculate. How? When I say algebraic manipulation, like this. If, for example, you have X and Y or 1, right? How many gates you need? You have to Y or with 1. This is 1 gate. And the answer and with X, right? If this is function F, this will come F. But if you know the laws of Boolean algebra, you know that actually this thing will be, let's go to the students. What's the answer? Y or 1? Let's see who is listening. What's the answer? Nobody but you. Is everybody asleep? Sleeping?
No.
So what's
No.
the answer? I'm gonna. What's the answer? Why? Okay, then I ask question type. So now by using mathematics, I know this thing is actually equal to x and y. So instead of this, I can just draw this. X and y. Now I save this one, right? I don't need to use this one. This is just like an example, simple example. Now, later on, when the circuits became more complex, then there was a scientist called Carnot. Mr. Carnot came with this Carnot map. We call it K-map. Yeah, K-map, yeah. And this is good for like a small to medium size with 4 or 5 input. But what if your circuit has 10 input, 10, 20? What you gonna with that? Then you have to actually use the CAD software. Now this is another area that you actually can get the software from others. You can buy it, right? But what happens if they don't give you? Again, you see the problem? This problem all the time happens, all the time, in everywhere. So it's very important for you as an engineer that first you realize what's out there. Like there is a software called CAD that help you to simplify circuits, and plus it's important for you to know how to build one by yourself. Okay, so for the CAD, you can, oh god, you can use this called Espresso. Yeah, this one. So this is the algorithm, Espresso signature, a new exact minimizer. You see minimizer for logic functions? Okay. Means optimization, right? I give it to you. So if I click on this, I cannot read, right? But because you are Assumption University student, you actually can read it. We'll just go to Assumption University proxy, something like that. Yeah, off the campus, this one, okay? You can, it really doesn't matter where you live, okay? Thailand or outside of Thailand, doesn't matter. Through this proxy that I told you, right? You have to set your browser, okay? Connect to the campus. It means your IP, when you contact this website, right? Your IP is the Assumption University IP. They think that you actually on the campus, okay? And then you can read it. You can read this journal papers, okay? Espresso, okay. So the CAD software, right, uses Espresso. So now if you want to build the CAD software, you can actually go read this paper. An algorithm for exact two-level logic optimization that radically improves the Quinn-McCluskey QM procedure. Now you actually from here, you can learn what is this guy, okay? And then you can see this is actually an algorithm, okay? This is for optimization of logic gates. Can you see? And then from here, you can learn. You see there are citations. Minimization of Boolean function. All right. And now if they don't even give you the software, you can build one. You can write one. You just read this, okay? And you can build one. Okay, now back to here. So today we're gonna learn the K-map. K-map, this guy, the scientist, he's very clever, very clever. He realized that he can use the human's ability to recognize patterns, okay? Recognize pattern or pattern recognition. Humans can recognize patterns better than most powerful supercomputers. Can you believe that? That's why we can play chess. You know, and now we cannot beat the computer anymore. But a few years ago we still could. Now the computers are so powerful. Anyway, so what he did, he said, let us have a very interesting thing based on what we call the gray code. What is gray code? Look, this is, I want to encode or arrange the numbers 0 to 3. This is the normal one, right? 0, 1, 2, 3. Is that correct? No. The guy says there is another way that I can arrange this such that the binary equivalent value like this, okay, in that arrangement differs only by 1 bit. What does it mean? It means this guy is next to this guy. They only differ by 1 bit. Can you see? Let me zoom in. 1 bit. Can you see? So this is same. This is different. But only 1 bit is different. 1 bit different. Okay? Now take these two. Okay? This is same, this is same, this is different. Can you see that? Take this one. This is same, this is same, this is different. Okay? Now, so 0, 1, 2, 3. Now, what is this? 0, what is this? 1, what is this? 3, what is this? 2. So, instead of writing like this, you write 0, 1, 0, 1, 3, 2. Okay? Now, how about 3 bit? 3 bit is, if I want to arrange this in normal manner, is like this 0, 1, 2, 3, 4, 5, 6, 7. Okay? But if I want to arrange this in gray code, okay, is I write like I write them in binary, and now look, these two are the same, right? This is different. Only 1 bit. With the next one, look. This is same. This is same, right? This is different. Can you see that? How about next one? Same. This is different. Okay. How about next one? Next one. Same. This is different. And so on. Okay. So when you write like this, right, it becomes that thing gone again. So 0, 1, 2, 3, 4, 5, 6, 7. Now let's arrange this in gray code. It becomes 0, 1, 3, 2, 7. I'm reading from here. 7. What is that? No. Yeah. No. After 2 is 6, 7. What's this one? 5, 4. Oh my God. Look. Oh. Yeah. Look at that. So funny, right? But this is gray code. Means this one and this one differ only by 1 bit. 6 and 7 differ by 1 bit, right? Now, holy hell. How can I say redo? Okay. So now instead of doing like this, right? 1 row, I say let's do it in 2 rows. So 0, 1, 3, 2. 6, 7, 5, 4. Okay. So basically, what I did is this part, right? I just moved it to next line. Okay, it become like this, right? This one, right? I just move it to here. But look, then you see these scientists, they're very clever. So he observed, he said, if I do like this, then 0 and 6, look, 0 and 6, they differ by 2 bit, right? So it doesn't work. So he said, why I don't flip this? So he flipped it. So he came up with this 0, 1, 3, 2, and then 4, 4, 5, 7, 6. Wow. Can you see that? No. He just fit. Oh. He just reversed this like this. 4, 5, 7, 6. Now, if you write it like this 0 and 4. Look at 0 and where is 4? 4. Right? They differ only by 1 bit, only this bit. Can you see that? Wow. A great code, okay? No. Okay, look at this. So the goal here, so they only differ by 1, okay? So now it becomes 0, 1, 2, 3, okay? Now I just copy this 2 times. And you remember that one that I showed you? So maybe undo. Oh, this gone. But the numbers that I show you, if you remember, is the same here. 0, 1, 2, 3, 4, 5, 6, 7. Okay? I just show you how they make it. So it's actually this thing, right? Copied 2 times. All right. Now this pattern, you always remember this. 1, 2, 3, 4. Bing, 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 bing. Okay? Ding, 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 ding. I remember I learned this when I was 13 years old. Until now, I still remember. So means what? Let's start from 0, 0, 1, 2, 3. You see? 4, 5, 6, 7. You see? Bing, 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 bing. Then you will not compute. Bing, 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 bing. Bing, 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 bing. Bing, 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 bing. Okay? Now, when you get this, this is for 3-bit. How about 4-bit? We have the 4-bit too. 4-bit, you just copy this 2 times. Okay? So, look at this. Now, let's look at the 4-bit. Bang, 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 bang. 0, 1, 2, 3, 4, 5, 6, 7. But be careful. This come from here. 8, 9, 10, 11, 12, 13, 14, 15. Okay? Now, this is very important. Why we put them next to each other? Why? Look at the reason. Okay? Let's say I have a function that goes to 1 at this location and this location. The other location is 0. Okay? 0, 0, 0. Here and here it goes to 1. What's the mean term for 0? What is it? Look. If you remember the here, that's the mean term, right? For row number 0. What is it? A bar, B bar, C bar, right? For number 0. The function is 1. Means here, right? So this is the same thing. So the mean term is A bar, B bar, C bar. For this one, location 1, you actually can look at this too. It's actually easy. So it's A bar, B bar, C. Okay? So A bar, B bar, C. Okay? Now that's the function. So I just OR them together, and this is my function F. Okay? Now I want to optimize this by mathematics, Boolean algebra. Okay? Look. This thing is the same. This thing is the same. I factor them out. So I write A bar, B bar, and this is C bar or C. Correct? So this thing is actually equals to this, right? Now, can you tell me what's the answer? What should I replace this term inside the parentheses with? Let's go here. Tell me. 1, 1. Yes, correct. All this, correct. Let me give. Delta. Okay, correct. 1. So this is 1. Correct. Is there any student who doesn't know why? I think it's very easy. So what did I do here? What did I do? I have eliminated 1 bit. What bit? Only 1 bit. What bit? The bit that differs. Can you see? This bit differs. And by combining these two terms, I eliminate it. And I have an optimized term, right? That's why this scientist so clever. He said, I'm gonna put the numbers next to each other, and then by using my eyes, I can know which bit they differ, and I can just remove it by my eyes. So look at this. He said, if I put them like this in gray code, then I can quickly know these two are next to each other, right? So I group them. And if this is A, this becomes A bar. When I say A, mean this part is A. Then the above row is A bar. If this is B, this is B bar. Okay. If this is C, these two are C bar. Okay. Now, when I say C or C bar, B or B bar, what does it mean? It means, pay attention, this is very important. It means, let's look at the binary value 4. What is 4? 1, 0, 0. What is 5? 1, 0, 1. What is 6? 1, 1, 0. Now pay attention. Put the ABC on top of it. ABC. 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 Okay. Now in all these numbers, A is 1. Can you see that? That's why we say A. When you say A means this row, it really doesn't matter which value you pick. The A is 1. Now, this thing is A bar. Means it really doesn't matter which value you pick. If it's 0, 0, 0, A, B, C. A is 0. Can you see that? Here, 3, 0, 1, 1. Wait. What's the A? 0, 2, 0, 1, 0. What's the A? 0. So you see, that's what we mean. Now, let's get with this explanation, right? So if here you have 1, here you have 1, then you can group them, okay? And then you read it like this. This group is not inside A, right? It's not here. So this is A bar. This is B. This is B. But this green circle is not inside the B, so it's B bar. And can you say anything about C? No, because C, half of it is inside C, half of it is not. That's the one bit that differs, right? So you just don't talk about it. When you don't talk about it, it means you eliminate it. A bar, B bar. It's the same answer that I got here, but now I did it. A bar, B bar, you remember? Wow. So by my eyes, I can calculate. No need I write the equation. Amazing, right? Now there are some rules. First, you have to cover all ones, then the grouping is to the power of 2. They must be adjacent, all the ones, right? Then if you create groups with larger ones, it means you have more optimized circuit. You can share the ones. If it doesn't have any adjacent, then you cannot optimize. And then on the table, if you have the X, it means don't care. And the boundary cells mean these are the boundary, okay? Means the border, right? They are adjacent, means 0 is adjacent to 2, 4 is adjacent to 4, sorry, 4 to 6, 12 is adjacent to 14, 8 is adjacent to 10. That's what it means. Now, one example. This is now what's the goal? Optimize. If you don't want to optimize, this is the function, right? You find the min terms like this, 1, 2, 3. Okay, that's it. Now we want to optimize, so we use the K-map, and this 0 goes here, this 0 goes here, this 0 goes here. Be careful, okay? This one goes here. Then this goes here, this goes here, this one goes here, okay? And this one goes here, all right? Now, after you place 0 and 1s into the table, then you group. Now, is 3 to the power of 2? No, so I cannot have something like this because it's 3. So I have to look for the power of 2. So this one, how to write is inside A. You see it's inside A, so it's A, and it's inside C. The red one, right? It's AC. The green one is inside A and B. That's it. So this is the optimized version. Now compare which one is smaller. This one. This one need three input. Can you see? 3 input. And gate. This one need 2 input. This one need 3 input and gate. This one needs 2 input and gate. And plus this one needs 2 OR gate. This one needs only 1 OR gate. This one also needs inverter. Can you see the prime? The prime is inverter. And this one needs no inverter. So it's actually quite optimized. Really, very optimized. Now, oh, what time is it? 3 o'clock. So let's have a break, okay? Now it's 2. Do you have any questions regarding this before we go to break? Questions. Give me the questions. La 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 la. L dot audit. No questions. Okay, so let's have a break.
Sorry, Ajay.
Yeah, L dot. Yes.
I have a question, but it's not regarding the subject. It's about the grade.
What?
It's about the grade, about the reports number 1.
Oh, this subject? This subject, I talk about the course outline, right? Did I or didn't? I didn't.
No, I mean the reports number 1 that we submitted.
Can you see your grade or not?
Yeah, I can, but I think there is like a mistake.
Okay, if there's a mistake, just let me know. Yeah, just you can send me in chat room, in private. But if you send me in public, is okay too. Okay, but if you make a mistake, I cut more. But if I make a mistake, it's okay.
Okay.
All right. So just send me in private and say, Ajahn, I think question 1 or 2, you made a mistake. It's possible, yeah. Because I grade them very fast. I don't want to spend time. So yeah, so if actually I used to tell this in the first session. So I grade your reports very fast. So there is a possibility that I make mistake, but you have to double check, triple check. Okay, don't waste my time all the time coming. I remember before I had like 22 students per section, and they keep coming. Oh, John, this is a mistake. I don't want that to happen. Okay, so you check 3 times. If you think I made a mistake, you just capture the question and my remark. Before I used to mark on the report, but now I mark in the feedback. There's a feedback section. I just tell you which part I cut mark, right? For example, I say question 3, there's a problem, cut half a point, something like that. So just tell me that, okay, I cut wrongly, and then I adjust, okay? But if you are wrong and I'm right, then I cut again, okay? Okay. It's just because I want to minimize, okay? So if I made a mistake, just let me know. Now, let me see what time is it, 2:7. Let's see each other again at 3:07, okay? See you. See you. Bye-bye. Okay, let's continue. This is very cool. You know, when you go to 7-Eleven, right, in Thailand, get this one. Oh, can you see it? You cannot see it. This one. So good. When I was kid, like 5, 6 years old, I really like this. I still like it. What do they call it? It's like hardened jelly. In Iran, we call them pastil, because I think the first brand was pastil. Oh, this is made in Indonesia. Cool. Okay. You are recording this meeting, you know? Okay, so now we learn how to minimize. What's next? Next is totally different topic. Maybe after 20, 30 minutes, the session will be over. Maybe 30 minutes, let's see. So, where are you? Where is my pen? Here, okay. So first of all, if we have a signal that changes, okay, like this one. When the signal goes from low to high, okay, this you see, this, we say to this edge a positive edge. It's a positive edge occurred, okay. And when it goes from high to low, we say that's a negative edge. See, negative edge. Now, if I have a circuit here, circuit number 1, and then another circuit number 2, and this circuit number 1 sends a signal to the second one, sends a signal, okay? We say circuit number 2 is triggered, okay, by circuit number 1. Now, if circuit number 2 is sensitive to positive edge, means it does something, it gets activated, it turns on, or it performs an action or something, whatever, okay? We say the circuit number 2 is a positive edge trigger circuit. Means in order to activate it or to trigger it, you have to send a positive edge, okay? Or a negative edge. That's it. Now, let's look at this one. This is a bunch of logic gates connected together. But there is a very special case here. The output is connected to the input. So there is a feedback. Can you see that? It's not like a normal combinational circuit that we learned before. Okay. Now, beside that, we have another thing here, a clock. What is a clock? Clock is a sequence of pulses, a square-like pulses like this. That's a clock. This is a clock. That goes up and down, up and down, up and down in periodic manner. Same intervals, okay? Now look at this. If you can actually put 0 here, K0, J0, okay, and then try to predict what happens to this output. So how, for example, if one of the inputs of an AND gate is 0, the output is 0, right? You really don't need to know this. You don't need to know. And you can actually go and see the behavior of this circuit by looking at Q. Here we show the behavior. If j is 0, k is 0, when the positive edge of clock comes, you see, so it's the detector. When it detects, for example, you put 1 here, means I detected already. Okay? Then the system or the circuit latches to the previous value. Means the Q will not change. If it's 0, it will be 0. If it's 1, it will be 1. It locks to the value. And that's actually a memory. Later we will learn this in details. Okay, this is a memory. Because it locks or holds the information, memory. Now, you can see, I can set and reset this memory. If I have this combination of JK, the Q will be 0. This one, the Q will be 1. And if I have both of them, this is the special case that we will use. Set to 1, then the rising edge of the clock here comes. The output Q will toggle. Means if it's 0, it becomes 1. If it's 1, it becomes 0. Okay? Now, when we learn this circuit, I can actually copy another version of this here. Okay? And then connect the Q to the clock of the second stage. And now what I did is I just created a 2-bit counter. Look, here, if I set this to 1, when the clock like this comes, this thing go up and down, up and down, up and down, counting, right? And then this thing is connected to here. This thing, output of this also go up and down, but it goes like this. So if the clock here, the clock is this, so it go up and down like this. Okay, now the second stage go up and down like this. Can you see that? Why here? Because this is the rising edge. Rising edge, rising edge. So rising edge, it flips or toggles. Can you see that? It toggles. So by connecting this, we call this JK flip-flop. JK flip-flops together, I can make a counter. Okay. Now, if I have a 2-bit counter, I can count from 0, 0, 0, 1, 1, 0, 1, 1. Okay. If I have we call this mod 4. Okay, this is mod 4. If I have only 1 bit, I can count 0, 1, 0, 1, 0, 1, and so on, right? This is mod 2. Mod 2, mod 4. If I have 3-bit counter, I count from 0, 0 all the way to 1, 1. This is called mod 8. Mod stands for modulus, modulus 8. If I have 4-bit counter, I have mod 16, and so on. Now this counter 0, 1, 2, 3 can go up or can go backward, down. So mod, for example, 8 up counter or down counter. Okay. Now there is an IC that we can use for counting. The IC number is 7493. So go to here, TTL IC 74 series. Go to Wikipedia. You see we have a lot of ICs. It's huge. Can you see that? What we want? 7493. 7493 here. That's the description. 4-bit binary counter. But in parentheses, it says divide by 2 or divide by 8. So that's the mod 2 and mod 8 that I told you. Mod 2 and mod 8. Now, look at the datasheet. Click here. You can access, let's go back. Access all the datasheets here. Can you see that? You can open any one. 7493 is this one. We open this one. Now I can see 3 pinouts. Which one is ours? 7493 is the third one here. 7493, you see? 7493, this is the pinout. It means I can actually buy this IC. From eBay, no, from RS Component. 24 baht. It's a little bit expensive. Okay. When you buy it, then let's find some space. Here. This is the IC. This is the semicircle. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now, imagine that we have this IC, but now we are not in the lab, so we cannot have it. But you have to give me a project, okay? So you have to actually, most of the students, they make digital circuits. Sorry, digital clock like this. And this, what we are learning today, is the basis of that. So probably you are going to give me something like this, okay, for your final project. So you have to learn this, okay? You buy the IC. This is 7493. The first thing is that we have to know about the power. Where is the power pin? Go here. Pin number 5. Can you see that? So it means after you get the IC, you connect this to VCC, which is 5 volt. What's the ground? Ground is pin number 10. So this pin should be connected to ground. Okay. Then what are the output of the counter? This one, QA. You see? QA is pin number 12. Can you see that? So QA. Why Q? Why Q? Because if you pay attention, here when I show you the JK flip-flop, can you see the letter Q? The Q. So it's basically the output of this flip-flop Q. But you have 4, so you must label them Q, A, B, C, D, because it's a 4-bit counter. So QA, be careful, next one is not QB, is QC. So it's not order. Then Q, I forgot, let me check. QB is here. A. Next one, or this one is D. This one is D, be careful. This one is D, and the QC is here, okay? Now, it means I can actually get QA, QB, like this, QC, and QD, okay? And connect them to whatever I want. Let's say to, this is resistor, LED. I need 4 resistors, okay, 4. And this is what? Ground. Same ground here, okay? So if you do like this, then you actually can drive these LEDs, and these LEDs will show you the counter value, and you can see something like this 0, 0, 0. And the next time the pulse comes, pulse is connected to where? CKA. CKA. So you have you have to connect this to clock. I will tell you later how to generate this. Okay, this clock. Every time that you have a positive edge like this, right? This counter goes to the next value. Becomes 0, 0, 0, 1, 2, 3, 4, 5, 6. That's a counter. Okay. Now .2, and there is two important pins here, R1 and R2. Can you see? R01 or R2, R02. So what are they? I am going to find the table that talks about them. Here, it says if both of these reset pins are high, 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 then the output is 0. L means low. 0, 0, 0, 0. If one of them is low, then you have normal operation, you count. Look, because of that, I can actually connect only one of them, but to be more sure, I connect both of them to ground. Okay, now this is how you connect this IC, but there is one thing missing. Now look at the schematic of this IC inside datasheet. Where is it? Dun, 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 dun. Ah, here. So this is 7493. It has this schematic on the rightmost. Here. Look at this. Here you have the J-K flip-flop, but it doesn't show you that this J and K is connected to 1. It's actually connected, okay? So Q, A, B, C, D. But pay attention. QB, let's zoom in, is trace connected to the next plug. Now tell me, is it negative edge trigger or positive edge? What do you think? Negative, Eldad is right. Because of that bubble. Can you see the bubble? So if it doesn't have the bubble, it means positive edge. If it has a bubble, it means negative. Same as inverter. If you have like this is a buffer. If you have this bubble here, means you invert it, become negative or inverted, or yeah, what's the another word for invert? Yeah, invert, flip, toggle. Okay. So this is the same thing. Here we have a bubble. Okay, we have this small circle here. Now, as you can see, the QB is connected to next station, but QA is not connected. This is because by design, this IC want to give you three options actually. 1-bit counter, 3-bit counter, or 4-bit counter. Okay, so basically I have the same thing here in the lecture note. Look at this here. So this is the mod 2 1-bit, this is mod 8 3-bit. Now what happens if I want a 4-bit or mod 16? What should I do here? Can you tell me? Here, this one. This is inside the IC. I have 1-bit counter, 3-bit counter, but I need 4-bit. What should I do?
We need to add one more JK.
Type so I can see and give you more. Type. Chat room. What should I do here? Add one JK flip-flop? No. I just explained already. What should I do? But I give a point to L dot for participation. What should I do? Nobody? Oh my God. Means you don't listen, okay? You see? This for this 3-bit, I have 1, 2, 3 JK. I connect this to here. Connect this to here. I need 4-bit. I have to connect this to here. Now it's 4-bit. This is 1-bit. This is 3-bit. I just connect it, become 4-bit. Does it make sense? No. So remember, I have to connect the QA to clock input B, right? Can you see that or not? Look at the datasheet. QA to what is input B? CKB, clock B, right? I have to just get a wire and connect. Now, when you get the IC, this is the IC, right? A lot of students, they set up this and they see it's just 3-bit or just 1-bit. Okay, the reason is that they forget to connect QA. You have to have a wire, jumper wire. Okay, connect this to this. This is CKB to pin number 1. You have to connect this. You will get a 4-bit counter. If you don't do, you will get a 1-bit counter. Okay. This pin not connected. This pin NC not connected. You see? Wow, this candy is so good. I cannot stop. Pin number 13 NC not connected. So get a wire from QA connected to CKB. It becomes 4-bit counter. Now, do you have any questions? We finished. Now I'm gonna explain the experiments. Question? Okay. So the first experiment, you live in, you work in very cool factory, and then they say, "Oh, you remember the alarm you did last week? Now you're gonna produce that for 1 million factories." Mass production. It means even if you can optimize one single logic gate, you're gonna make one. Let's say one logic gate is 1 watt. You're gonna save 1 million watts. Is it like that? And if they give you 10%, means you're gonna get 100,000 baht as an engineering optimization job. Optimization actually is very important in engineering. Now, when it comes to, like, look at the clock. You see, why do you think they have these curves here? Or when you look at the can, right? If you look at the bottom of the can, this is the, so they can actually make something like this, right? But if you, next time that you drink, right, you pay attention to the bottom. The bottom has a convex like this. It goes inside. It has like a hole inside, right? That you don't see. Why? Because they don't want you to. They don't want to give you this much of drink. And instead of giving you like this, right? Almost all of them, they have a curve like this. All the drinks, because they want to save this, right? They don't want to give you this. There is actually the material that they use for building this bottle is also the most optimized is this. So you can actually look at it. Can you see the curves? Can you see the curve? The curve? Why they have the curve? Have you ever wondered? Or now you cannot see the bottom of the can. It goes inside. Or here, can you see the curves here? The curve. Or why is it like this? All of them is because of optimization. Okay, all of them. Now, the alarm system. You remember P0, P1, P2, and then you alarm if 2 or more of them fail. This time you have to optimize it. So what I expect from you is this. You give me the truth table, the K-map, a schematic on your simulator, and that's it, and the waveform. So you have to pick a simulator that can generate waveform so I can see, all right? This is the first experiment on your report. You don't need to do it now. I finished the session and then you can do it wherever you like. And then if you have questions, you can ask me during the week. Now, pattern generator, what is it? Usually I ignore this, okay? But now I'm gonna have a bonus point. So you actually can do this, but I tell you how to do it. So first you have to find a simulator that can simulate TTL IC chips, like 7493 is the chip that you want to simulate. See if you can find or not. I'm not sure really. Okay. If you can find this, then I show you the pinout like this, okay? Then connect, simulate like this. Connect this to ground, exactly like this. And connect for LED and capture the waveform, okay? It should show me the waveform from 0, 0, 0, 0 to 1, 1, 1, 1, 1, okay? Now, if you cannot find, then I have the datasheet here, right? I show you already. Just go to the datasheet here. That's it. Yeah. And then you can actually see the real schematic. What's inside that IC? You can see here. Then your simulator should have JK flip-flop, okay? Negative edge trigger. So you just put 4, and then this is a NAND gate. This is the reset, right? Reset goes to clear. This is the clear pin. And set up this. If you can make this happen, I give you bonus point. If you cannot, then it's okay. I don't cut mark. Because I know this is actually a little bit advanced. We are not supposed to set up this circuit now. This is big number 2, okay? 0, 1, 2, this is the third big, okay? So as a beginner, you are not actually expected to do this. This is advanced, okay? But try. If you could make that happen, it's okay. If you could not, then don't worry. Plus, you have to have a clock generator. Now, this is optional. Optional. I will give you bonus point. This one, what is this one? BC to access. So, in old days, in order to use less hardware, they instead of 0, 1, 2, 3, 4, the BCD, they use XS3. What is XS3? everything that, every digit that you have, you just add 3, plus 3. And excess come from excessive, it's excessive. It has extra 3 points. So if I want to show the 0, instead of 0, I show the 3. This means 0. If I want to talk about 5, 5 plus 3 is 8. So I just show or true or use 8 instead, okay? So there is a mapping involved here. From 0, 0, 0 to 0, 0, 1, this is 3, right? Binary. So 0 actually is 3, and so on. Now, this is actually a good practice because here, you see, after 9, we don't have any BCD, so we don't care, right? Now tell me, if you want to set up this, how many output this circuit has? Can you tell me? Tell me the number of outputs of that circuit. BCD to XS3, what do you think? Output? This is so good. L dot is clever. What's your GPA, L dot? L dot GPA.
2.7.
What?
2.7.
2.7 only? Why? You 2.7? That's the problem, you know. I think our assessment is wrong. We have a lot of good students that they deserve 3.5, 3.6, but the way that we assess is kind of like we put them down. But I can see a lot is clever. He answered my question very fast. 4. It's correct, 4. You see? So if we have 4 output, I can name them F3, F2, F1, F0, right? Okay, and then I have 4 input. I can label them A, B, C, D. Then what I have to do is draw a K-map. I think you just need 30 minutes to finish this, okay? And I said this is F3. And I look at this column. Okay, the green column. And I just put the values here like this. Ding, 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 and so on, okay? So in order for you to not make a mistake, I suggest you to divide this thing every 4 rows like this. Okay, so the first row is all 0, so I just put 0, 0, 0, 0. Second row 0, 1, 1, 1, 0, 1, 1, 1, and then 1, 1. Now the rest I don't care, so I just put like this. Don't care. Okay, and this is A, B, C, D. And then I start to optimize. I might, yeah, this is A, and maybe like this, and maybe like this. Anyway, up to you, okay? Then I will get the equation for F3 equals to something. Then I repeat this for F2, for F1, for F0. So you need to give me 4 equations and 4 K-map, okay? And then now you have this circuit, right? Then run your simulator and you have the equations, right? Draw the schematic. Draw it, okay? Now what you have to do is, this is the input 4 and the output 4. Then you prop all the inputs and all the output, and you give me a waveform with 8 channels, okay? So I can see the 4 input and 4 output, that's it. Now, if you were in the lab, this is called pattern generator for a reason. Because this is actually a counter, right? It counts from 0, 0, 0, 0 all the way to 1, 1, 1, 1, right? So basically, I can actually use it here. A pattern generator. I just put a counter, and this is Q, A, B, C, D, Q, A, B, C, D, okay? And then what happens here? I just generate the 0, 0, 0, 0 to 1, 1, 1, 1 here on this bus, on this lines. And I can see the output, and I can test it. Okay, and this thing, when I do like this, it becomes unit under test. UUT. Okay, but you don't need to do it because now we are not in the lab. So the only thing that you have to do is to give me a waveform with 4 input and 4 output. Any simulator that can generate waveform is fine, and that's it. If you don't have any question, we will close this session. And there are some 4 questions. Okay, answer the questions. It's not that difficult. Put it in your report. Do you have any questions?
No, sir.
No. Okay. So good luck to you. If you have questions, you can ask me in Microsoft Teams. I check it all the time. See you. See you next week.
Thank you, Achan.
See you.
Thank you.
Buy this one. This is so good. Believe me. It's like 30 baht something. I don't know how to show you. Oh, here. Can you see?
Yes, I can see.
I hate that.
Maybe I show here. Hey, buy this one. It's not good for the teeth. You have to brush your teeth right after that. It's low quality. See you.